Dear friends, in my lecture 2 of the electrical engineering series, I will discuss about the basic concept of the Kirchhoff current law and voltage law. So before going to the discussion of the Kirchhoff law and voltage law, we must understand some terminology about the basic element of the circuit like node, junction, branch, loop and mesh. So all these quantities and terms are explained with the help of the circuit shown below. So in the slide you can see I have shown a circuit diagram where two batteries are there and three resistive element R1, R2, R3 are there. So node is a point in a network where two or more than two circuit elements are joined. For example, in the diagram you can see A, B, C. Three are the circuit nodes where two or more than two branches are connected. So now coming to the branch. Branch is the part of the network which lies between two junction nodes of the circuit, like AB. AB is the branch of the circuit where resistor R1 lies. BC is the branch where R2 lies, and BD is the another branch where resistor R3 lies. And DA and CD are also the another branch of the network. A closed path of the network is called a loop. Like if you can see in the diagram ABDA. ABDA is a closed loop, okay, closed path. Similarly, BCDB, also a closed path considered to be a loop. Now coming to the mesh. Basic elementary form of the loop that cannot be further divided in another loop is called a mesh. See here in the diagram, if we talk about the outer loop, A, B, C, D, A, that loop can be further divided in two other loops, ABDA and BCDB. But if we talk about the ABDA, that cannot be further divided in another loop. So the basic elementary form of the loop that cannot be further divided in another loop is called mesh. Junction. So junction is a point in the network where more than two or circuit elements are joined. So it is the point where current is divided. So this is the basic difference between the node and junction. If we talk about the A and C point, these are the node point of the circuit. But if we talk about the B point is also a node, but that is considered as a junction because here current is divided in different parts. If we assume a arbitrary current from even battery, that current will be divided in two paths passing through the R2 and R3. So this is a clear-cut difference between the node and junction. Junction is a point where current division is possible. For example, B and D are the junction as shown in the figure. D can sometimes we are not considering as a loop or junction because we are considering loop node D always as a reference point. So German scientist Kirchhoff given two basic laws after doing so much analysis of the network interconnections. So first law deals with the flow of the current, that is called KCL, Kirchhoff current law. Another deals with the voltage drop in the closed network, is called KVL or Kirchhoff voltage law. So first we'll see the KCL. So definition of the KCL is that the algebraic sum of all the current at any node or at any junction of a circuit is zero. Summation I is equal to zero. For example, suppose we see the circuit diagram as shown in the next slide. Here I have taken a node denoted with a yellow color, and it is having so many branches. Like some branches are having the current towards the node, and some currents are flowing away from the node. So this is a node point where we are having the adjoining of the so many circuit element, and we can find out the division of the current. So you will have so many incoming current and outgoing current. So at that point of the circuit, we can apply the KCL. So algebraic sum of all the currents at this node point is zero. We'll go to the previous slide. So the one notation is there, the direction of the incoming current to a node is taken as a positive, while the outgoing current are taken as a negative. We can take vice versa also. We can take direction of the incoming current as a negative and outgoing current as a positive. It depends upon our choice. So for example, again we go to the next slide. I have written one equation as per the notation discussed in the previous slide. So we can see the diagram again. So many currents are there. So if we see the circuit diagram properly, we can find out that I1 is a incoming current. So it's a plus quantity. I2 is also a incoming current plus I2. I3 is a outgoing current minus I3. I4 is a outgoing current minus I4. I5 is a outgoing current minus I5, and finally I6 is a incoming current, so plus 6. So according to notation, this equation becomes I1 plus I2 minus I3 minus I4 minus I5 plus I6 is equal to 0. So if we segregate the positive term and negative term on the left hand side and right hand side, then we can find out the another equation written as I1 plus I2 plus I6 is equal to I3 plus I4 plus I5. We can see that I1, I2, I6 are the incoming currents and I3, I4, I5 are the outgoing current. So based on this equation, we can conclude that sum of the incoming current is equal to sum of the outgoing current. So this is the basic fundamental concept about the KCL. So according to KCL, the algebraic sum of the current entering a node must be equal to the algebraic sum of the current leaving the node in a electrical network, or basically sum of the incoming current must be equal to the sum of the outgoing current. Now discussing about the KVL. So KVL states that the algebraic sum of the voltages or voltage drop in a closed network that is transverse in a single direction is 0. In other words, if we say the algebraic sum of all the EMF provided by the battery and the algebraic sum of all the voltage drop across the circuit component is 0. That is denoted by the equation summation of E, that is the EMF provided by the batteries, all the EMF of the batteries, plus summation of the voltage drop in the circuit element. Circuit element may be resistive, inductive or capacitive, but here we have taken the resistive element only. So summation of E plus summation of V must be equal to 0. So here, by understanding the concept of the KVL, another notation is made here, that we will assume that current I causes a positive voltage drop when flowing from a positive to negative potential, while negative potential drop when current flowing from negative to positive potential. So generally current always flows from the positive terminal of the battery towards the negative terminal of the another battery, and current always flows from the higher voltage to the lower voltage. We'll understand the concept of the KVL with the help of the one circuit diagram. So it is a mesh, you can see, because it cannot be further divided in another loop. So it's a closed loop, considered as a mesh. So here we have two batteries V1 and V2 and two resistive element R1, R2. So here we have taken arbitrary direction of I, that is flowing in the clockwise direction in the circuit. So from the orientation of the battery, we can find out that both battery V1 and V2 are connected in a additive mode. Means combined mode, it can be written as a V1 plus V2 combined battery, because here positive sign of the V2 is connected to the negative sign of the V1. So both battery are connected in a same phase, in the same direction. So it will be added. So if we write down the KVL equation here, so we can write down in the term like minus V1 minus V2 plus IR1 plus IR2 is equal to 0. Or in other way, in the second equation, if you write down sum of all the battery with algebraic sign V1 plus V2 is equal to all the voltage drop. So here you can see in the second equation, V1 plus V2 is equal to I into R1 plus R2. So from here we can find out the value of the I, that is given by V1 plus V2 divided by R1 plus R2. Suppose polarity of the any of the battery, for example, V2 is reverse. Just we make the connecting direction of the V2 as a reverse as shown in the figure. So in that case, V2 will be taken as a negative. So second equation can be written with algebraic sign V1 minus V2 is equal to I into R1 plus R2. So in that case, current equation becomes V1 minus V2 divided by R1 plus R2. So first we have to see the orientation of the batteries, whether both are connected in serial manner or in opposite manner. So if a positive sign of the first battery is connected to the negative terminal of the second battery, then both battery are connected in a serial manner. So in that case, both battery voltage value will be added. But if any of the battery terminal, positive terminal is connected to the another positive terminal of the battery, so it both will be in opposing manner. So in that case, lower voltage battery will be subtracted from the higher voltage battery. So according to that, current direction will also be determined, because current always flows from the higher battery to the lower battery side, means higher potential to lower potential. So according to that, current direction will also be reverse. If we see the another example, in that two batteries are there, just like you can see V1 and V2, and both are connecting in opposite manner. Means positive terminal of the V1 battery is connected to the positive terminal of the V2, and 3 resistive elements are there, R1, R2, R3. So initially there is no current, but we have to assume one arbitrary current. So we have assumed one arbitrary current as a clockwise direction in the circuit that favored the effect of the V1, because I told you in the previous example that current always flows from the higher battery to lower battery side. So I have shown the current direction as a clockwise direction that is favoring the effect of the V1. So initially we will assume that V1 is higher than V2. If we know the value of the V1 and V2, so current direction will be as per the higher potential to the lower potential. It may be opposite that I have taken in the diagram. So here we have assumed that V1 is greater than V2. That's why current direction is in the clockwise direction. So if we write down the equation in a mesh according to the KVL, so minus V1 minus of V2, because V2 is connected in opposite direction. So it will affect a negative voltage. So minus V1 minus of minus V2 plus IR1 plus IR2 plus IR3 is equal to 0. Means sum of all the EMF provided by the battery, algebraic sum of all the EMF of the battery, voltage drop in the circuit, that is equal to 0. So this will be modified as written in the second equation, that V1 minus V2 is equal to I into R1 plus R2 plus R3. So again we can find out the value of the I, V1 minus V2 divided by R1 plus R2 plus R3. So suppose we will get a positive sign here, means V1 is greater than V2. So whatever current direction we have assumed, that is correct. But if V2 is higher than V1, so in that case we will get a negative sign. Getting a negative sign in this calculation doesn't mean that we have done a wrong calculation. It means whatever direction of the current we have assumed, actually it is in the reverse direction. So some point I want to discuss that should we remember while we are discussing about the KVL and KCL, that KCL states the summation of the current at a junction that remains 0. According to KVL, the sum of the electromotive force and the voltage drop in a closed circuit remains 0. Second point, while applying the KCL, the incoming current is taken as positive and outgoing current is taken as a negative, as we have discussed earlier. Similarly, while applying KVL, the rise in potential is taken as positive and fall in potential is taken as negative. This is very much important point, rise in potential and fall in potential. So we go back to the previous slide. So in this diagram, you can see we have written here minus V1 and minus V2, and plus IR1 plus IR2 is equal to 0. So here we have taken minus V1 and minus V2 because V1 and V2 will provide some current when it is connected in a closed loop. So whenever current is flowing through the battery, there is a fall in potential. After some time, voltage across the battery will be reduced. So there is a fall in potential across the batteries. That's why these voltages are taken as a negative. But if we talk about the R1 and R2, initially we don't have any current across the R1 and R2. Initially current value increases from 0 to the I value. So initially voltage drop will increase across the R1 and R2. That is called rise in potential. So rise in potential is taken as a positive. That's why this equation is written as minus V1 minus V2 plus IR1 plus IR2 is equal to 0. But in the other manner, if you write down the sum of all the EMF with their sign is equal to all the voltage drop in the circuit. It will be given by V1 plus V2 is equal to IR1 plus R2. So it depends on your choice whether you want to apply the rise in potential or fall in potential concept or the second concept. Third point is about the basic concept that KVL and KCL helps in finding the analogous electrical network and impedance of the complex system. So basically by using the KVL and KCL, we can solve the very typical complex system in a very simple manner. It also determines the current in each and every branch. Ultimate goal of applying KVL and KCL is to find out the voltage drop across any circuit component by calculating the current flowing through each branch of the network.